starting to think about the uses of the products of the aldol condensation. And this is really indicative of what we do for the rest of the term, is just put things together to go other places, to start with simple building blocks and start to build them up into more complex systems so that we can then do biology or polymer chemistry or whatever else. So will the molecules get more complicated? Yes, necessarily, because we're heading in that direction. But the chemistry really won't. If you keep a track of this stuff, we've been tracking this stuff in recitation, we'll do the same today, trying to stay organized, trying to stay on top of it, trying to understand the differences between the different molecules so you can make informed decisions about what to do mechanistically. This isn't so bad. And it should start to get interesting as we start to apply it to subjects that you're more familiar with. And you'll see that organic chemistry really is central to an awful lot of things that you'll be doing in the future. This introduction of the alpha-beta unsaturated aldehyde or ketone, which is the species on the right. And we build these things from aldehydes and ketones by doing aldol condensations. So typically you would start off with some sort of molecule that has at least one alpha proton. For this you need two because you need to take two off. And you heat this stuff up in a solvent that has a base and a polar protic solvent, and away we go. We get an alpha-beta unsaturated aldehyde in this case. Now the key feature for these types of systems is their polarity, the idea that you can think about having charge in different places. So at the bottom I have three pictures, the first of which is the sort of typical way you draw an alpha-beta unsaturated system, and then we split the ketone or the aldehyde, and we draw this classic plus-minus resonance structure that shows why the double bond is so polar and why this thing undergoes reactions with nucleophiles. And everybody's happy with the fact that a nucleophile will go there. We've done that, ad nauseum with all sorts of different nucleophiles. What we now need to worry about is the fact that having that second double bond in there is going to make a difference in terms of the electronic characteristics of this system. We can see now that this is allylic. If you look at that there, that's allylic. We dealt with that quite a bit a while back. And you will draw this third resonance structure in which this N carbon becomes positive. Overall, that leads to delta positive here, delta positive here. And you have an electrophile now that has two places that can be attacked. The idea now that the system can be attacked at two places, that starts to open up things in terms of synthetic utility and also mechanistic ideas in terms of what can happen and what will happen. And we have to deal again today with the idea of kinetic attack and the idea of thermodynamic outcomes and talk about stability of products and then think about how to use them. So what we'll do first is conjugate addition, this idea that we can attack these things either at the carbonyl carbon or at the beta carbon to produce different products. And you've got to be on your toes here to be able to see the difference. So we start off with two classic examples of organometallic chemistry. The first one we know quite well, the addition of a Grignard, something here such as phenyl magnesium bromide, and this undergoes attack at this carbon here. Now, it doesn't show it on this slide, but I'll put the numbers in. That's atom 1, that's atom 2, that's atom 3, and that's atom 4. And if we label the enone as such in this case, we can start talking about 1,2 addition versus 1,4 addition in a similar sense that we did for 1,3-butadiene a while back, but it's opposite now. In that example, the double bonds are behaving as nucleophiles. In this example, the double bond system is behaving as the electrophile. So we've switched the roles. And we find now that if you react this system with a Grignard, you get attack at the 2 position, at the carbonyl. Now, is that reaction reversible? No, it's not going to come back because that Grignard is a lousy leaving group. So that's stuck. And the question will be, why does it go there particularly? And the answer will be because that's the most positive carbon. It certainly is more positive than the beta carbon. So the fastest reaction, the kinetic outcome, which will be detailed again in a second, is attack at the carbonyl to do a nucleophilic addition, and that's it. It's stuck. Then you would quench and you have your alcohol. We've seen that a bunch of times. There will be different reactions, and this one's a bit of an odd one because we can change the reactivity of the organometallic by putting copper in there. The problem with this reaction mechanistically is it's not that well understood. It isn't a direct nucleophilic attack, and some people think it's radical chemistry. So we tend not to worry about learning this one in the sense of the mechanism, but we do understand that this goes to the beta position. So there's something about the electronic characteristics of this thing and the presence of this double bond that allow the copper to guide the R group into the beta position. You would see that at a more advanced level. You might see it on a graduate level, organic class, but at this stage we don't worry about it too much. But it does give you an alternative in terms of synthesis. If you want to make a molecule that's branched at the 2 carbon, add a Grignard. If you want to make a molecule that's branched down here at the beta carbon, add an organocuprate. And we can make organocuprate simply by taking RLi and adding some copper iodide. And we can do that quite easily, and that gives us this reagent which adds in the opposite sense. So that's just defining the playing field. You will see this a lot in the practice problems. If you want to go 1,2, do a Grignard. If you want to go 1,4, do a cuprate. Now that 1,2 versus 1,4 isn't immediately obvious. It is at the top. There's atom 1, we added something to it. There's atom 2, we added something to it. That's a 1,2 addition product. The 1,4 addition product isn't immediately obvious. We have to sort of work out where that comes from. But those two reactions are very useful synthetically, and you'll see them a lot. Now, to get started on this idea of kinetics versus thermodynamics, we have to have some idea of why the reactions will happen, where the reactions will happen, and whether those reactions are reversible or not. And so the only difference in these two setups is that we're dealing with carbon nucleophiles, but one of them is very much more reactive than the other. We've seen cyanide now. Cyanide's a salt. You can actually put it in a bottle and it'll last forever. So Cn- is not unstable. It's reactive because you can make good bonds from it, but it's not unstable. Whereas the reaction at the top, or the reagent at the top, is very unstable. This thing will degrade over time. So if you think now about reversibility possibilities, if the R group over here adds at the 1,2 position, it's done. That's it. It's not coming back off, and that's the end of the reaction. And we'll call that the kinetic process because that's where the faster reaction happens and because of where more of the positive charges. At the bottom, we have the classic example of cyanide. Now, cyanide, like we did for addition of cyanides to ketones, it can add and it can break back off because it's not a bad leaving group. So we'll see that this one down here is reversible. This one isn't going backwards. Might make a note of that. We'll develop that in a second. This one can go backwards. And if you can go backwards and forwards, you can get to an equilibrium, and that equilibrium always favors the best outcome. And we'll see now that the 1,4 addition product, again, it's not immediately obvious yet where that comes from. It will be in a second. That 1,4 addition product is thermodynamically favored. And the simple answer is because you get the carbonyl back. You want that carbonyl back because it's worth more than the double bond up here, right? It's about 170 for the pi bond down here versus 140 for that. It's a stronger bond, so you want it back. So what we need to develop now is this idea of how fast things happen, where things happen, and then whether the system is reversible or not. If it is, it will go to equilibrium, and you'll get the best outcome possible. This is pretty heavy, but ask questions as we go. So I put this slide together a while back to try and summarize the differences, and then I'll break it down into its components, and we'll do it step by step. I have two different possibilities here. I'm starting with the same enone. You see with the enone, alkene, ene, one, ketone, enone? This is being attacked in two different directions, in two different ways. On the left, I have attack of a Grignard. It seems to be going to the 2-carbon to give 1,2 addition. On the right, I have attack with a cyanide. It seems to be going to the 4-carbon to give ultimately what's called the 1,4 product. So I need to detail this in terms of the mechanism. And the key here really is that this reaction does not go backwards. This one can go backwards. If that's the case, you can get to equilibrium. So we start off with the simple one that we just did, the Grignard experiment. Grignards are very powerful nucleophiles. They're very unstable. They will not last very long. They certainly won't last in the presence of an acid. And if we add the material here, I'm going in this direction, don't forget. I'm starting with the enone. I'm going to here now. I get classic 1,2 addition. Why is it going to that carbon? Well, that's where more of the positive charge is because it's right next to the oxygen. So the fastest reaction is going to happen right there. And you'll find now that that sticks. It does not come backwards. The faster reaction is called the kinetic reaction, the lower activation barrier, and that's stuck. So that's not going to come back, and that's the end of that. So whenever you see a Grignard with one of these alpha, beta, unsaturated systems, you go for the ketone. You go for the carbonyl carbon every time. Now, the opposite of that is the thermodynamic possibility here, where we can get equilibration. So that's going to show where we have something like cyanide and a whole bunch of other nucleophiles that are about to show up that we've seen something of, but we'll use them now in more detail. So we have some cyanide. We have a polar protic solvent. We can use that polar protic solvent as an acid without necessarily having to add any acid. We can use that at the end to pick up an enolate, for example. So what's happening here, and this flow of electrons should make sense. I'm transferring the charge from carbon to oxygen. I'm kicking into the beta carbon here, pushing electrons up, and I'm putting the charge on the oxygen. That gives this species down here. What's that at the bottom? What is this part of this molecule here? Say again? Enolate. That's an enolate. Right? So we've made this enolate, and then enolates don't tend to last long in protic solvents. They're quite unstable. They want to be protonated. That's a very fast reaction. So what tends to happen then is protonation. And we will form this. Now I want to point out the 1,4 addition product here. Starting out with this system where that's 1, that's 2, this is 3, and that's 4, I have now added material at the 4-carbon down there, and I've added material, the hydrogen, at the 1 atom, the oxygen. So that now is the 1,4 addition outcome. You'll notice that it's a more highly substituted double bond, so that helps. And also when it undergoes tautomerism, you get the ketone back. And don't forget with ketones, the ketone form is heavily favored. You get very little of the enol, it changes into ketone quite quickly, and that's it. So you'll get lost here a little bit if you're not careful. You do addition at the 1,4 positions, and you get the carbon-carbon bond formed in that position right there, and that is not the actual product. That is not what you isolate. That is going to tautomerize and give you this ketone back. So the key difference in these two reactions, if I now go back to that first slide and try and summarize both of them together, is when things happen, okay, and where things happen. In the first reaction, it's very fast to attack at the 2-carbon because that's very electrophilic. And in the second reaction, the key feature here is that it's reversible. And if that's the case, you go for equilibrium and you get the best possible product, in this case, which is the ketone. Make a point to keep an eye on the enol and tautomerize at the end. So what we're doing here is a reaction called a Michael reaction, in which we are adding a nucleophile, and it seems to prefer to go to the beta carbon, not to the carbonyl. It might go to the carbonyl first, but it will back off. And this then requires a certain type of nucleophile, a stabilized nucleophile, that is able to also serve as a leaving group. So in this first step, what we're doing here is we're adding the nucleophile to the beta carbon, and we're producing this intermediate enolate. That enolate is in the presence of acid. You do these reactions often in protic solvents. So it will pick up a proton, even if it's from water or methanol, something like that, and it will give you the enol. And that's fine. But the problem is that when people are not concentrating, they stop there. And then the next addition might be the addition of a Grignard. And they wonder, well, I've got an enol and I've got a Grignard. Surely an enol might protonate a Grignard. And they miss the point, the fact that this has changed from that very quickly into this. And you can see now where a Grignard would go there in a multi-step synthesis. So be aware of the fact that once you get to the enol, you must tautomerize it and get back to the carbonyl species so you can go further on. That's very, very important. So now we have a pretty useful reaction from knitting together pieces of carbon. And in the next few slides, as we introduce the Robinson annulation, you'll see the beginning of a steroid synthesis, how people develop synthetic steroids. And a lot of this relies upon making 6-membered rings. We'll do again recitation where we talk about the possibilities of what can happen in these systems and why it prefers to go in one direction. And the answer usually is because that's the most stable outcome. And you can see now typically we're using these types of things, 1,3-diketones. The 1,3-diketone here is special because it has protons in the middle, which are more acidic than regular ketone. We should be aware of the proton on a ketone is about 19 pKa, and you put it between 2 carbonyls, it goes to about 10 or 11. It reduces quite dramatically. So when we draw resonance structures for this, we ought to be able to recognize that if I take that proton off with a base, I can spread the charge over here and over here. I can draw 3 independent resonance structures to show that this is a pretty good molecule. And therefore, it should behave as a leaving group. So there's a sort of a classic setup. You'll see this, if you're doing it in KOH, you might do it in water as the solvent. You probably have a proton available anyway. This last step I'm not completely happy with, but I'll explain that a little bit as we go through. You may not have to quench this stuff. So at the end of the day, we get these materials, and you start to add things together to make bigger frameworks. And that bigger framework can then cyclize and maybe go further. I'll show that in a second. One of the limitations for this is going to be the fact that ketones aren't very good at this. You need that 1,3-di system to make this work. And you need something called a Michael donor, which is the nucleophile, and the Michael acceptor is the electrophile. And again, as Piers says, the nucleophile might well attack here first, but it has the ability to break off because it constitutes a decent leaving group because it's resonance stabilized. And so what we'll do here is nucleophilic addition, but at a different place. We'll do a conjugate addition away from the carbonyl, ultimately to push electron density up to the O again. So what we're interested in here is the type of molecules that will do this. And they look an awful lot alike. There shouldn't be too much of a leap now in terms of understanding or learning. There's a very simple one. Here's a very simple one. We dealt with those when we did the acetoacetic ester synthesis and the malonic ester synthesis. And we can see now that if you have 2 electron withdrawing groups flanking a CH2 group, those protons on the CH2 group become acidic, and you can take them off, one at a time. Down here, we saw that with the acetoacetic ester synthesis. We didn't see this one, but I think it's logical, right? That cyanide group right there is electron withdrawing. It ought to be able to stabilize the negative charge through resonance, so it has the same properties as the ones that we've seen. We haven't seen a lot of this one, but it will do that type of chemistry. And again, I would put this one in a box and just sort of make sure you're aware of the fact that the mechanism isn't quite the same, but it gives you the same outcome. In terms of Michael acceptors, in terms of what's being attacked, the electrophile, make sure you make the differentiation over here. These things are the nucleophile, and this thing over here is the electrophile, and then it's simply a matter of remembering where it goes. I have an alpha-beta unsaturated aldehyde. I have a ketone version here. This little R group over here makes no difference whatsoever. The chemistry is the same. I have this alpha-beta unsaturated ester. This will work likewise there. The amide works. This nitrile works, and this nitro group works. So again, just look for a pattern. Look for the double bond to be directly next to an alpha-beta unsaturated, or next to an electron withdrawing group, and then we'll get nucleophilic attack at the beta position. So with those in mind, we can start to think about limitations here and think about why this works in certain systems and why it doesn't in others. It does work very, very nicely. And this is the way you would run these reactions. You would use one of these di-activated systems in which you have two electron withdrawing groups. It does not work very well for singly activated systems like that, for ketones. And the answer is a bit more in depth than the book will give you. I think it gives you one line about the fact that it doesn't work, but the answer is because we get polymerization. The answer is because the products that you get here tend to react with the starter material again and again and again, and you get bigger molecules than you want. And I'll deal with polymers 2 weeks from now, but that is one of the limitations of these reactions. So we don't use these simple systems. We tend to use these more complex systems, right? But you'll see in a second these are very, very useful. So this isn't a very good reaction, and at this level we typically wouldn't do that, right? At graduate level you might put some different groups on there to make it more viable, but here no, we typically wouldn't use ketones. So with that in mind, how do you get around some of these problems? If enolates are not very good at this, how do you make an enolate equivalent undergo this type of reaction? And this was work developed by Gilbert Stork, who is, I think he's still going, born in 1931. He's up at Columbia in New York. And he developed the enamine synthesis. We said we'd come back to enamines eventually. This is where we do it. And what we're going to do here is develop a surrogate of an enolate. We're going to develop something that acts as an enolate, but it isn't, but it then becomes the same product that you would get if it was an enolate. So it's behaving as a surrogate. So what we'll do again is think about aldehydes and ketones as electrophilic. We'll think about having an acid in here. So if I have an acid in there, what should I do first? I think I'll protonate something. And then we'll attack with the nucleophile. There's the nucleophile. And in particular here, we have chosen a secondary amine because that produces an enamine. Again, you don't have the balance at H2O with this. You have one proton, so you have to go get a proton from somewhere else. And if you remember the mechanism, the last step is deprotonation at the alpha position. And that was before we did alpha carbon chemistry. Now it should make sense and add up. So we'll get this enamine. And the whole point of the enamine is that it's nucleophilic. We'll see now that enolates are quite basic. You produce them in quite basic solution. There are some limitations here. And they are quite reactive in the right circumstances, but they don't work very well in this Michael addition. So Stork came up with the idea that the enamine behaves an awful lot like a stabilized or modified or, let's use the word, tamed enolate, right? The reactivity is calmed down a little bit to make it work in this reaction. And the idea is, if you look at the enolate structure, we always draw these two pictures. We always draw one in which the charge seems to be on the O and some of the charge seems to be on the C. And that's related to the fact that the O can push electron density into the pi bond. We've seen that multiple times now. If we think about nitrogen being the same, nitrogen's, more nucleophilic than O, but this is a neutral species. So it's not going to be as reactive as an enolate, but it's going to serve the same sort of purpose. So we can see here, pushing electron density into that gives you a species which is nucleophilic at the alpha carbon. So if I were to draw that on this picture, I would put delta negative on that C. That's the nucleophile. And again, think about the possibilities here. We're pushing out from a double bond. The nitrogen's helping that happen. And if you had an oxygen there instead, if you had an O here instead, that would not be as nucleophilic because O is more electronegative, holds its electron density better. So the N is in between. So the N here for the enamine is somewhere in between the reactivity of an enolate and an enol. And it turns out they work spectacularly in this type of Michael system. So we'll make enamines again. Go back and look at that chemistry, make sure you're okay with that. And they work very nicely, and they serve as an enolate. So here we have the nucleophile. It's attacking the beta carbon again. It could attack the carbonyl, but it'll break back off because it's a decent leaving group as well. And we produce that species. That looks an awful lot like where we just were in terms of nucleophilic attack. And then we have this, and then we hydrolyze. Now, this again is kind of an abbreviation. I'm not too happy with the way that's drawn. What is happening in that change, in that overall bottom reaction? Protonation and hydrolysis. So there are two things happening in here, and I would probably label that and sort of spread it out a bit so you have more of an idea what's happening. There's actually two processes happening in that one step. The first one is a very fast acid-base reaction to give you the enol, which then tautomerizes to the ketone. The second process is then getting rid of the N through hydrolysis. That takes longer. Okay, so that would be left to go in a flask. And I would point that out on an exam. I would say, these are two steps. What are they? It's kind of summarized as one here, which I don't particularly like. But at the end of the day, you get the same product you would have gotten if you did a Michael addition with an enolate. That's the key. What's the difference with the early ones? The early ones had the second carbonyl right here, which was fine. That works perfectly. now you've got some surrogate for the enolate, because the enolates don't work very well. So the Stork enamine synthesis is very clever chemistry. It's been used a lot for natural products chemistry, and it's very reliable. So if you want to use a 1,3-diketone, great, just start with that. If you want to use the enolate, you have to do the Stork chemistry. Here is a typical sequence related to what people just said. If you want to make this type of molecule, and you understand that this is a ketone precursor, the way to go is through the enamine. And so that means you need to temporarily turn the ketone into the enamine by doing hydrolysis. And it's an equilibrium process, so think about how you might do this. The byproduct is water, so how do you drive the equilibrium to the product? Get rid of the water, magnesium sulfate, distill it, whatever idea that you've seen before. And then we put in the alpha beta unsaturated system, the Michael acceptor. And then we go after it, and again, keep an eye on this fact, the fact that this prefers to do attack at the beta position to give the ketone back. And again, this is, I think, a little bit misleading, so we'll fix that. And you get this material, in which you've now put these two pieces together through that bond. And as you're making, we've called them flashcards, some people call them study sheets, whatever you want. Focus on the bonds that you're making. Okay? Don't try and memorize structures, but focus on the chemistry and where things are happening. Because again, this is all about the alpha carbon of one compound attacking someplace on the electrophile. That's really what you need to focus on to keep a track of stuff so you don't get lost. Very useful chemistry. Now, in terms of using this for synthesis, sure. It's, you know, people throughout the world do this in terms of this class. We should be able to handle things like this. Can you build a molecule using this chemistry? There are plenty of practice problems. I've said this in recitation this week, and I'll say it again. If you go into the course pack, you'll find all sorts of old exam questions that relate to the final. I never put a final up, okay? But I do have lots of old exam questions from old finals. If you want to go look at them, they're all I've marked on there which chapter they're related to. You should recognize what chemistry it is and have plenty of practice to be able to get ready for 2.5 weeks from now. So in terms of using this, here's a starter material. It's a ketone. Doesn't work very well in this Michael chemistry. And we want to turn it into that. Now, how do you recognize what chemistry you need? Well, you understand what bond is being formed. That bond is being formed in that reaction. So that means one of these carbons must be an alpha carbanion, must be an enolate, and the other piece here has to come from the alpha and beta unsaturated system. Once you see it, it's not a difficult pattern to learn. So thinking retrosynthetically, we're breaking this thing into two pieces. Again, it's all plus-minus chemistry. There are no radical reactions here. We're going to go back to one being a nucleophile and one being the electrophile. So this is just a pattern you can see, and you can start to use it in a forward direction. So to make this work, you would start off with ketone. You'd turn it into the enamine. In this case, it was biased because only one side can form the enamine. And then you attack the alpha-beta unsaturated system, followed by a workup, and that gives you this. So you have a very elegant way now of making this type of system, which is a 1, 2, 3, 4, 5 dicarbonyl system, and they're useful. This is I think the pinnacle of this chapter. This is my favorite reaction in the chapter, and it is very, very useful for making steroid backbones. You think about the use of steroids in all sorts of different medical applications. These things are important, and so people have modified these things over the years by doing synthesis. And you need to start out by understanding that 6-membered rings are absolutely vital to medical chemistry or medicinal chemistry. What we've done here is we've taken a typical donor, the system that can give you the negative charge, and a typical acceptor, the alpha-beta unsaturated system, and we've tied them together. That first step is what we've just done. I'm going to build it up here and then show you everything in one step, everything in one slide. So you can see how complex this is, but how you can manage it. And then if we take this further, maybe you can isolate this stuff if you want to, but then if you heat this stuff up, you get the condensation. So it's just an aldol reaction followed by the elimination. And that gives us this. And this is a 6-6 system, which is the backbone of a steroid. Steroids always have this, or tend to have this 6 system where you've got 6 like that, you've got 6 next to it, and then you've got 6 up here, and then you've got 5 up there. Have you ever seen the structure of cholesterol? Classic structure. So to make that first system, this is how we'll do it. It's something called a Robinson annulation, putting 2 rings together. First part we've already done. Second part we have to worry about. It's nothing more fancy than an intramolecular aldol, in which this carbon here becomes nucleophilic, and it goes after that carbon. In recitation, we're developing this to say, well, as people have said today, can it do this instead? Can it go to this part of the molecule instead? And the answer is yes. But that direction might not give you the best outcome. You might end up with the wrong size ring. You might end up with a 3-membered ring instead of a 6. If you can go backwards, you'll work your way back and go back to the 6-membered ring. That should be obvious by now. So to get this started, this is from the website. It's just simply a depiction of that reaction, an intramolecular aldol reaction. But you can use this type of question to make sure people understand what's happening. I have a polyfunctional molecule right now. And even the simplest molecules in biochemistry, like amino acids and peptides, they're polyfunctional. Carbohydrates are polyfunctional. That's where you need to be in the future. I have a choice here. I can take that proton off that carbon, but I also have a proton on this carbon that can come off. And I also have a proton here that can come off and a proton there that can come off. And the question will be, why don't they come off in other places? And the answer is, they do. But if you take off one of those protons, let's say at this position, and you make that carbon negative, that negative charge in the aldol reaction wants to go after some carbonyl. That's the whole point of that reaction. In that reaction, it can only really go here, can't it? Yeah? If it attacks across there, what size ring do you get? 4. That's terrible. So that's not going to happen. Well, sorry, correct that. It can happen, but guess what? It will break back off because that step is reversible. And ultimately, you'll find that taking the proton off this end gives you this anion, and that cyclizes to give you a 6-membered ring, and that's preferred. So it's all about sort of going down here and down here and down here, but ultimately finding out that over here is better and working your way that way. So the steps here require concentration. You've got resonance structures to worry about all the time. You've got intramolecular attack. Is that fast or slow? Fast, because everything's right there. Everything's there. You don't need to go find anything. Intramolecular reaction here gives this anion. That anion then, don't forget, we're in solvent. That is protic. We do have some protons around if we want them. Not H plus necessarily, but H delta plus. We can go deprotonate the solvent, and that produces this. And then on this reaction, this is fine because this looks like the E1CB. We take off the proton next to the carbonyl, and then we eliminate. And that gives us ultimately the double bond. So we go back to an alpha beta unsaturated system. And that 6-6 system then is nicely functionalized to do other things. You can build off from there and build the steroid system. So be careful here. There's nothing new about that. It's just an aldol reaction. So I put this up. There's one mistake on here I'll point out in a second. You might be able to see it already. I'm starting out with a different system, but I'm going back a bit. The previous slide was all about already being here. We've already put the two pieces together. In this reaction, I'm putting those two pieces together and then cyclizing. So this is the bigger picture. I have, in this example, a potential Michael donor. I have a Michael acceptor in the presence of base and a protic solvent. So I do have some acid around. If I deprotonate, I have choices. I can deprotonate here, I can deprotonate here, and I can deprotonate there. Why do you think we're favoring one place? It's between the two carbonyls, therefore it's more acidic. That should be obvious. I see 3 resonance structures to describe why that's a decent species when we take that proton off, but then it's nucleophilic and it sees the enolate here. Now, I think I'm missing an arrow from this one actually. I think I need to have an arrow that comes in and does something like that. Nucleophilic attack at the beta carbon in the same way we just did. That produces, I've turned it around, but that produces the same type of structure that we've already drawn. That's an enolate. And I pick up that proton, and that gives me ultimately the ketone. So you're going to form an enol, then it goes to a ketone. What process is that? Tautomerism. That should be in there by now. You should absolutely be happy with that stuff by now. But then, I'm still in basic reaction medium, and we still have acidic protons. And especially if you heat this thing up and force it to go further and let it go longer, you will get the cyclization happen. So the first reaction that we just dealt with stops there. Let's put in the two pieces together. If you do it at low temperature, you can often stop right there. Now I have a choice again of where to take off a proton. There, at the end over here, and also over there, which is the same as over here. And it should be obvious now that you're going to take the one off that leads to the best cycle. In this case, it will be a 6-membered cycle again. So take off that proton, form the resonance stabilized enolate, that then cyclizes. Why not cyclize over here? It's the same thing. It would be the exact same thing. And if I deprotonate elsewhere, my cycle will be too small. I'll get a 3 or a 4 or a 5-membered ring, and a 6-membered ring is much better. So then we deprotonate, and again, here's the problem. This is out of date, E1CB. We deprotonate first at this position, and then we kick out the leaving group. So make a note of that. And at some point, I'll fix that slide. Let's think about what we've just made and the utility of these compounds once we get there. We can see now the sort of progression from chapter 21, 20, 21, 22, and eventually into the latter chapters. Things get more complicated because you put more functional groups in there. And what we've just done is we've said we can take things like ketones and turn them into this type of dicarbonyl. But it's not just any old type of carbonyl. It is such that the carbonyls are situated in set patterns. And you'll see later that biology does this too. I just made some slides yesterday for the biosynthesis of this massive antibiotic that we're going to talk about in class next week. And all the ketones are lined up 1, 3, 1, 3, 1, 3, all the way down because of the logical chemistry that gets there. So in this case, the outcome is a 1, 5. Not 1, 4 or 1, 2, but 1, 5. Because of the disposition of the alpha carbon here and the carbonyl there. They happen to be, this carbonyl happens to be 5 atoms away from the other one when you put the chemistry together. So with that in mind, summarize some of the things we've seen. If you want to build a 1,3 system, do an aldol reaction because your products end up 1,3 to each other. And let's say you wanted to take this and you wanted to turn it into a 1,3 diketone. What would you do to it? PCC, absolutely. You'd oxidize the thing and you get the ketone right there. So you can get to a similar compound in which you've put the things in, particularly where you want them. If you want esters, you want the disposition to be 1,3, you do this reaction. What is that called? That is a Claisen reaction. Yes, you should recognize that by now. It's a Claisen reaction. So we have some very simple ways now of building materials, very much like biology does. And the same synthesis I was talking about yesterday uses this Claisen reaction again and again and again and again to build this huge, great macrocyclic antibiotic. So biology does this, and we can do it in the lab. So to summarize some things, I'm almost done with this chapter, and I'll get into 23 and get the boring stuff out of the way first. If you want to go to the 2 position, what do you add? If you want to put some carbon functionality at that 2 position, what do you add? A Grignard. Yeah, a Grignard every time. If you want to go to the 4 position with a carbon-based material, you use a cuprate. Now, the book hasn't mentioned this, and I'm going to sort of try and fill that in. There is a lot happening between here and here. But the outcome actually is the enolate. It's not simply nucleophilic attack, but you do get the enolate as the outcome. And if that's the case, when you quench, you form an enol, which then tautomerizes, and that's just a simple way of alkylating at the 4 position. But down here, we have something on top of that. Similar to, Michael, this is what you asked before. If you do this chemistry carefully, and you start out with attack at the 4 position, and you get the enolate form right there, enolates also alkylate. So you put something here, you can use that intermediate enolate as a nucleophile. And that ends up with a dialkylated system. Simply by quenching, not with a proton, but with an alkyl group. Everybody knows that mechanism. What is that second step? SN2. When you head to biochemistry, which is many of you, and whatever they say about biochem not being a prereq, it is a prereq. You should take it here before you move on somewhere else. You will do much better later on. Biochemistry is all about nucleophilic additions. It's all about Claisen reactions. It's all about this type of stuff. So that language that you've been picking up cannot be forgotten. All this sort of gibberish about alpha, beta, and saturated ketones sounds great. You'd win at Scrabble. But it is important in biochem. And when the scale gets much bigger and you don't have time to explain all this stuff, you've got to know that. So be on top of this stuff now. So this last slide from that chapter, really, in terms of chemistry, is trying to explain why this cuprate reaction isn't as simple as it might look. It is, I think, beyond the scope of where we are at in the class. And it's giving you an idea here of organometallic chemistry and how useful it is, but also how different it is. It is certainly different to the classic stuff that we've been doing. And you can see here now the copper is being used to bind to the double bond. That's a whole world in itself. Hopefully in the next year or 2 we'll have a class on this stuff and people can take that in great detail. It's very, very powerful. You form a cuprate down there, and then all of a sudden it seems that the methyl group gets transferred. That's obviously not just a nucleophilic attack. So put this next to this slide. You're not concerned about that here, but if you've got some interest in this, some interest in organic chemistry in the future, medicinal chemistry in the future, these are the types of things you want to be looking at. Certainly if you go to a PhD in this subject, you'll learn these reactions. Very, very powerful. So it's not as simple as it looks, but that's roughly what's happening. You're not concerned about that mechanism right now. You're not going to be tested on that mechanism. We're trying to fill a gap. 23 is largely stuff we've already done. It's just summarizing it in a place for amines for themselves. And amine chemistry starts to get very, very interesting and very useful for medicinal chemists or pharmacy type people. An awful lot of medicines contain nitrogen. So we have to have ways of putting nitrogen into systems. We'll see some reactions that do that. And I have this slide just to try and summarize how complex this stuff can be. You've seen compounds like this. This is a reserpine, I think, and this is morphine, and this is penicillin G. These are obviously useful medicines. And they all contain nitrogen. And if we want to build those analogs and build new examples of this, we have to have ways of doing nitrogen chemistry. And this goes back to before World War II. Robinson got the Nobel Prize just after World War II, but most of his chemistry was done before that, in the 20s and 30s in Britain. Brilliant. Imagine in 1920, no NMR spectroscopy. You had very minimal tools, very, very sort of simple tools to be able to tell what you were doing. And if you're building up systems like this doesn't look that complicated at the top, but this is a biomimetic synthesis. This is trying to mimic what nature does. They'd worked out what nature does to build this type of cycle, and now they're trying to show that in the lab. How does it work in the lab? Can we compare it with nature? This is 1917, right, during World War I. So he won a Nobel Prize for this. This type of compound here is a tropane type system, which is found in cocaine and various types of analgesic compound. Very important chemistry. And he got to know this guy, RB. And Woodward is arguably the best organic chemist that ever lived and might ever live. Absolute genius. And he, again, using very simple tools, no NMR spectroscopy, no crystallography like we have now, built ridiculously complex molecules like this down here from scratch. It's absolutely world-class stuff. So amines now are very important. They're nitrogen-containing compounds. I'm going to get this out of the way now. The simplest example of this is ammonia. You all know about ammonia, how important it is to nature and how we have to recycle this stuff. And it is not organic, but it is the center sort of structure for organic amines. And if we swap out one of the hydrogens from an amine, from ammonia, and we put one group on there, one carbon group, we get a primary amine. And we did this when we defined the enamines and the imines. If you put two R groups on there, you get the secondary amine. And we've already seen these, not in great detail, but we have. If you put three on there, you get a tertiary amine. And they're very useful as bases. So, examples of these things. You should be starting to get interested in this now if you've got any aspirations of pharmacy or medicine, and even polymer chemistry or that for the engineers. Adrenaline, okay? Amine, secondary amine. Noradrenaline, primary amine. The body will convert this into this by demethylating. You can even think of that methyl group, it's on there, it can be taken off like a protecting group. Biochemistry does the same sort of stuff. And you go back even further, get rid of the OH, you get to dopamine. Very important neurochemicals. So amines are incredibly central to biology. In terms of their reactivity, this is just reviewing what we've done. They are nucleophilic and they are basic. On the left-hand side, in the presence of an acid, we should be protonating. We've seen pyridine as a base. We've seen triethylamine as a base, picking up protons. And if you have some electrophile and no protons, then you'll do a substitution reaction. What mechanism is that? SN2, because they're nucleophilic and they will attack simple systems to do that. And then finally down here, it's all based, all the chemistry of these things from now on will be based on the fact that that nitrogen has a lone pair and we can use it to go other places. We have to worry about names. This is trivial. This is why I'm doing it now quickly. Ethylamine, couldn't be more obvious, right? Isopropylamine, cyclohexylamine. If it has the word amine at the end of it, guess what it is? It's an amine, right? Gets more complicated, head towards biology, stereochemistry. Go back and look at RNS, it's on the final. This is going to be an exam that makes sure you learn something out of the 2 chapters or the 2 semesters of organic chemistry. We have stereocenters. We have a whole bunch of different functionality. There's the way we name this. The 2 there is to tell you where the amine is. Simple enough. Over here, likewise. In this case, look out. We've got to be careful here because the amine has that and the ol has that. Slightly different in terms of their names, but very similar structures. Examples from nature, examples from pharmacy, stuff like that. Paraaminobenzoic acid is starting to look very much like a pharmaceutical type structure. On the left, you've got 4-aminobutanol. So which is more important in this molecule, the amine or the ol? The ol. So if it's a substituent, we call it amino. Bromo, iodo, fluoro, amino. It's easy enough. And then down at the bottom, if you want to stick this onto a benzene ring, we remember aniline from the past. We've now got M-chloroaniline. Benzene chemistry is very central to this final. 5-ethyl-2-fluoroaniline. They should be fairly straightforward. There's nothing tricky about those systems. In terms of the others, you've got to put all of the groups on here. And in this example, I've got ethyl-methylpropylamine. Why does the methyl go in the middle? Alphabetization, logical again. Diethylamine, if they're the same, should be obvious. Triethylamine, if there are 3 of them. Then there's a way of doing this systematically. It's nothing more than you've seen, and I think you're okay with that. You can do that yourselves. In terms of their geometry, structure, they have 4 things attached. You might think that these things are chiral, but they're not. And the idea with these systems is that this is able to invert. These are actually flexible. And we get something called pyramidalization. It's like an umbrella blowing in the wind. You ever see that? Where it gets caught and it goes out? It goes backwards and forwards like that. And because it's flexible like that, unlike carbon, you can't get a rigid configuration. It can't be stuck as S or R. It goes backwards and forwards. So we don't see chirality typically at N. And that's exactly what that is.